welcome back to I Teach You Science. We're working on cluster questions for Earth and Space Science today again, and we're on this cluster about Thea and the moon today. Please share this video with all of your classmates, your friends, your teachers, so we can get the cluster practice out there for everyone to help study for the test. All right, let's see what we got here. I'm going to rate all these questions on a scale from 1 to 10 in my subjective opinion on how hard I think they are. So far in the last video, we did come and we hit a 10, and it was a really terrible question. So go check out that video and see how you do. If you want to print these out beforehand to try, I have the file in the description, so you can click it, do the questions first, and then come back and watch the video and me explain everything. All right, here we go. So it says Thea and the moon. The giant impact hypothesis is the most widely accepted theory for formation of the moon. Shortly after Earth formed, a small planetary body called Thea collided with the Earth. Some remains of Thea were included in the Earth's interior. That's interesting. Okay. So let's start underlining some stuff. So it says Thea collided with the Earth. All right, that's important. And then we also want to say something about some remains of Thea were included in the Earth's interior. Other remains formed into a ring of vapor, dust, and molten rock. Eventually, the pieces clumped together or accreted, forming the moon. Okay, so there was some of Thea that was then part of the Earth later on, and then some of it formed the moon. Okay. The late heavy bombardment is a period of time when the Earth, moon, and other inner planets experience intense impact activity from asteroids and comets. Okay, so this is just when there was a lot of impact activity. These impacts created cratered structures on the Earth and the moon. This is believed to have peaked about 3.9 billion years ago. So we can assume at this date there was lots of impact. Okay, the model below shows the information of the impact, and we'll see what they have here. So this is saying Thea hit the Earth. 20 hours later, you could see clumps of Thea sort of clumped in with the Earth, but a lot of this is still all shrapnel. Like, this is all what they said up here, the remains, right? Forming into the ring around there. And then we have a month later where the clumps started solidifying. Right there, you could still see there's still clumps of Thea. And now our moon is there. The moon is insanely close, 14,000 miles away. And then 4.5 billion years later, so a very long time later, we have our established Earth, right? Our remnants of Thea, which is that material in there that has now fully, there's no more like random particles there. Everything's sort of stuck together. And then the moon is now 239,000 miles away. Okay, so let's see what they can ask us about this. Use the model to explain how the collision of Thea, which eventually formed the moon and changed Earth's composition, occurred at different spatial and temporal scales. Okay, we like these words. You know why? Because they're so easy. So spatial would mean we need data over a distance. And then temporal scales, we need data over a time. So in our spatial answer, we have to mention a distance. And then in the temporal change, we just have to mention a time frame. So that's pretty easy because guess what? In here, we looked. Let's circle all the times. Look, we had 20 hours, 1 month, 4.5 billion years. So we could talk about that. And then for the distance stuff, we have this here, the 14,000 to the 239,000. So that's how we have to think about this. So this is spatial. Oh, no, I'm lying. This is temporal, temporal, temporal. Nope. Temporal, temporal, temporal. Here, spatial, spatial. Okay, so now let's see if we can figure this out. Spatial change. So that's the moon's distance. So we could just say and we're going to use the numbers in our answers here. So we could say the moon moved from 14,000 miles away to, and then we could look up here, 239,000 miles away. Over 4.5 billion years. And now really, honestly, I could have included this time in temporal, but it just made sense in my sentence to add that. And then for the temporal change, we could say like between, it took 4.5 billion years for the clumps of Thea to fully accrete or fully clump together. We could say that. We could say it took 20 hours for between the pre-impact of Thea to the post-impact Earth. But it's saying, it's saying at any point from pre-impact to present day. So we could say anything here. So let's do that. Let's do actually, I like this 1 month because that makes me be able to talk about how a lot of it clumped together. So let's say between post-impact Earth and early Earth, we'll say in the 1 month span between post-impact Earth and early Earth, the clumps of Thea began accreting in Earth's interior. And you don't even have to say accreting. You could just say, like, started clumping together. Started, sticking together. That's what I'm talking about, like this area and this area. So there. I mean, there was plenty of answers we could have said for the temporal, but that's what I just went with. So this question is so easy. As long as you know spatial and temporal, which you should. That's a 2 out of 10. That's super easy. All right, going on to, we got 4 different impact craters. Uneven rim edge with shallow middle depression in crater bottom. Okay, missing parts of rim edge with multiple smaller craters inside crater bottom. Small craters visible on weathered, less distinct rim. And then we have a distinct rim of crater surrounded by ejected material with a deep middle depression. Okay, I don't know what they're going to ask about this. All right. Which table identifies the correct relative ages of 2 craters and a piece of evidence that supports the hypothesis for the late heavy bombardment? So we already know the late heavy bombardment means tons of impacts in a short period of time. So, and they want us to compare oldest versus youngest craters. So first we're going to look at B compared to A. And we're going to try to figure out which is older. So B to A. Look how crazy this looks. First of all, there's all these extra stuff here. So this is definitely older. B is older than A. So is that true in that one? Yes. So this section is right. I don't even care about this evidence yet. I'm going to come back to that. We're just going to look at the oldest versus youngest for all of them. B compared to D. B, look at that. All weathered. D, that looks fresh. So B is definitely older than D. That is also correct. Okay, oldest C, youngest A. So C to A. C, A. A looks way fresher. There's more craters around the edge of this. This looks all smooth around there. So A is definitely younger than C. So that's also correct. Is this all of these going to be right for this part? And then oldest C compared to youngest D. So C to D. C to D. This one's definitely younger. There's way more activity here. So I would say this one's younger. D is younger than C. Yeah, okay. So all of that is correct. So now really this question is, which of these pieces of evidence is probably true? Okay, let's see. Craters of all ages cover most of the moon's surface. I guess. I mean, maybe. Multiple smaller craters are found inside the bottom of larger craters. Okay, wait, we have to rethink this. Evidence for late heavy bombardment, we need a lot of impacts. So ages is not going to help us prove that. So I would say now that's wrong. Multiple smaller craters are found inside larger craters. I don't know about that. I'll keep reading. The rims of the smaller craters are surrounded by younger ejected materials. I don't know about that. A large proportion of craters were determined to have formed over a short period of time. Yeah, that's what we want. A large amount of craters over a short period of time. The answer is 4. Yep, because we want tons of impacts over a short time, so that's definitely right. Construct an account. Oh, we got to rate that. That's kind of hard. This part was kind of tricky. I mean, I'm just assuming that I thought of that correctly. And this was from the reading. So, I don't know. I mean, really the only one that supports the reading fully is this answer. So that leads me to believe that you should have picked 4 just because of that being the best evidence. So I would say we'll call that a 5 out of 10. Construct an account using radioactive elements. Okay, so that's the reference table. And their decay products to support the giant impact hypothesis, which proves evidence that zircons found in moon rocks formed at approximately the same time as Earth. Okay, so let's go check our reference table here. Okay, so we're going to go down our reference table. We're going to go to our radioactive decay. All right, here we are. So we're looking for zircon, which we already had seen from the last cluster. So there's zircon and zircon. And now we could see right there, the half-life is about the same age as Earth. So now let's go back to our question. Construct an account using radioactive elements and their decay product. So I have to mention the element and the decay product to support the giant impact hypothesis, which provides evidence that zircons found in moon rocks formed at approximately the same time as Earth. So we could say, when looking at the radioactive element uranium-238 and its daughter decay product lead-206, having a half-life of 4.5 billion years, which is about the same age as the Earth. That's really all you have to say. That's what we're going to do. So we'll say the radioactive element uranium-238 and its daughter decay product, we're going to go look, lead-206 has a half-life of 4.5 billion years. When using zircon as a datable material. And that will cover it. So I would say that's an easy question because it's on the reference table, but just to sort of create a paragraph or a sentence about it could be kind of challenging. So I'd call that a 5 out of 10. A lot of 5s, a lot of middle of the road questions. Doable. All right, the model below shows some information about surface features found on the moon. So what do we got here? Terra, large impact crater, crater change, lava flooded impact crater, mare bridges. These are just features on the moon. Ejecta, that's remnants from an impact. And then we have surface Earth features model. So this is just a bunch of stuff from the Earth. Volcanoes, tributaries going into the river, a river delta, sandbar, depositional features. Okay. Let's see what the question is. We can go back up and look. A student made a chart of constructive and destructive geologic processes represented in the model of Thea. Okay. So constructive means something is being created. And then destructive, destroyed. Which table below shows an additional process that's correctly classified for either the moon or Earth and can be added to the table? So I don't really care about constructive or destructive. I mean, you could read this, but we know what it means. So now we're just going to see if that thing they wrote means that thing. So the waterfall weathers rocks and moves sediments along the river valley. Weathering is a destructive process, so this is wrong. Destructive, an upward flow of lava created, see? The Mare Ridge, that would be constructive, so that's wrong. Constructive, a delta formed from sediments transported by a river on Earth. A delta formed. Yeah, that could be a constructive because you just created a delta. Destructive, lava flows out of a volcano onto the surface. That's going to destroy. Now, they were going for this. I would say that's the answer to this. However, this answer here, in my opinion, could be argued because lava flow is going to solidify and create new Earth, like out of basalt. So I would say that this question really should be changed because this, in my opinion, is misleading. But that's just me. The volcano making new Earth. I mean, I understand that it's mostly destructive, but it could be argued. So we'll say 3. And we'll say this was pretty easy. That's a 3 out of 10. Number 5. Which 2 geologic processes have provided information about Earth's formation and early history by altering or destroying most of the very early rock record on Earth, while 4.2 billion-year-old craters on the moon still remain? The biggest difference between why there's so many craters on the moon and why the Earth doesn't have it is because we have an atmosphere. And our atmosphere has water and wind and all that stuff, so our atmosphere is going to erode a lot of material away and cover in all those impact craters. The moon doesn't have that, so that's our background knowledge here. So, plate tectonic activity and erosion of Earth's surface by water. See, that right there tells me that that's probably the right answer. Weathering of Earth's surface and accretion of vapor, dust, and molten rock. No, that made the moon. I don't know where they're going with that. That's wrong. Lava flows from erupting volcanoes and frequent earthquakes. That's not going to fill in everything. Those don't happen enough. Radioactive decay of the crust and decay of crustal minerals. That's just not right. So yeah, the erosion is going to fill in all those craters. So that one was pretty easy too. I'd say that's a 3 out of 10. Oh, we just got one more question here to finish this one. All right, let's just do it. The model below shows some information about the moon. The graph shows some information about seismic activity that occurs on Earth, earthquake data. The data table summarizes some information about seismic activity that occurred on the moon, like moonquake occurrences from 1969 to 1977. Okay, so there's moonquakes. Okay. Now, remember, the moon doesn't have plate tectonics or any of that stuff. So moonquakes are pretty much just from the expansion and contraction of the moon rock mostly. Like this moon is really, really thick rock, so that's going to crack and move over time, but it's not like plate tectonics. So let's just see what they have here. So they just have a data table. They're saying what the moonquake category is, how many of them happen. So we could see deep moonquakes are the most. All right, let's just sort of see what the question is. Complete each of the statements below to correctly describe geological processes related to the surface and interior layers of Earth and the moon. Place an X to indicate which phrase correctly completes the statement. So we're just going to go statement 1 and figure out which one is right. All right, 1 at a time. A comparison of earthquake depths and moonquake depths indicates all earthquakes occur at depths less than 700 kilometers in the Earth's crust and upper mantle. All moonquakes occur in a depth between 700 and 1200 kilometers. Let's see here. So here's your depth. 700 and 1200 kilometers, even 700 and 800, there's nothing above that. So that's completely wrong. So just by eliminating that makes this one correct. Okay. Number 2. Locations of circulation by thermal convection occur. Thermal convection does not occur in the moon. Does it say that? The thermal contraction and expansion, but there's no convection currents inside the moon. So that's wrong. But let's see what the Earth one is. Convection occurs in the lower solid mantle. Okay, so since the moon doesn't have thermal convection currents, the answer has to be this. I just think it's weird that convection currents don't occur in solids and they added the crust here. So I would say that this is not greatly worded. That's just my opinion. But the moon's eliminated from this, so it has to be that second one, but it's not a great question. The best evidence for the moon's formation from... I just want to go back to this for a second before I read that. The convection currents are mainly in the mantle and the asthenosphere area, and if we even go here, and we'll go to our reference table, right? What they give you. Like, look at this. The crust is... The continental and oceanic crust are solids. There's no convection currents in a solid. Circulation. I don't know about that. I mean, listen, I could be thinking about it wrong, but I'm pretty confident that's a bad answer. Number 3. The best evidence for moon's formation from a collision with a planetary body called Thea is the basalts on Earth and Moon are made from the same minerals. Yeah, I mean, the Moon, yeah, we have similar mineral composition as the Moon because it was part of the same collision. Sure. This one says the Moon and Earth both have a crust, mantle, and solid inner core. That doesn't prove how this planetary formation, the Moon's formation happened. So that one was very obvious. So I would say, doing process of elimination, this is definitely going to be the trickiest question, I would say. I'd give this a 7 out of 10. And a big star on that being something that I don't agree with. That is the end of the fall 2024 cluster. I will keep continuing to make more practice with Earth and space stuff. Hope you guys enjoyed it, and I'll see you on the next one.